Hey there, this is Mr. Wistar. In this lesson, we're going to talk about how to use recursion as a programming technique. Recursion is a very powerful method for developing solutions to various problems, but it can be a little tricky at first because it really requires you to think about solutions in a different way from what you're used to before. So I would encourage you in this lesson to expand your mind and try to think about things in new and different ways because it's going to be really different. We're going to talk about what makes a method recursive, and we're also, more importantly, going to talk about why you might want to use recursion in your programming solutions. And then we'll take a look at some of the more common syntax for writing recursive methods and some things you need to keep in mind when you're writing them in order for them to work properly. So what's recursion? You might have heard of recursion in some of your math classes, but simplest way of thinking about a recursive algorithm or recursive method is it's a method that calls itself. And that means that you have a method that is going to use itself over and over again. So you'll notice in this method here, if you look inside foo, down inside that else block, you'll see that foo calls itself. And we will see an example of that. So let's talk a little bit more about an example of using recursion. So in this example, we'll talk about how to use recursion to just count from one lower number up to a higher number. If you want to count from, say, 1 to 5. So in this case, if m is 1 and n is 5, then what you'll do is take the first parameter and compare it to the second parameter. If the first parameter is higher, then you don't have anything to do, so you're done at that point. So if I told you, for example, hey, count from 10 to 8, going up, you wouldn't be able to do that. There's nothing to do. So in that case, you wouldn't do anything. And that's called the base case. We're going to get to that a little bit later. But let's say that m is less than n. Let's say that you start by counting from 1 to 5. So m is 1, n is 5. In this case, you're in the else, so you're going to say the first number, so you're going to say 1. And then what you'll do is, and here's the recursive call, you will count from m plus 1 to n, or you'll count from 2 to 5. So in order to count from 1 to 5, I say 1, and then I count from 2 to 5. In order to count from 2 to 5, I say 2, and then I count from 3 to 5. And through all of that work, when we're all done, eventually we will have counted out 1, 2, 3, 4, 5. Now, granted, this is a really simple example, and it's not something that you would probably use recursion for. But we start with the simplest example just so you can understand what's going on. So, a couple things that you need to know about how recursive methods work. Every time a recursive method calls itself, it actually creates a brand new copy of the method running in your program. Some people think that when recursive method runs, it just goes back up to the top. Well, no, actually what it does is it puts itself on pause, and then it creates a new copy of itself and starts running that method from the beginning. And as soon as that copy is finished, then you go right back to the previous copy of that method and keep running from where you left off. Let's take a look at how that actually works in Java using the debugger. So here we have that counting method. It's going to count from m to n. It's the exact same code that you saw in the slides that we were taking a look at. But this time, I want you to, we're going to run it through the debugger, and I want you to pay close attention to the debugger window on the left-hand side. And in particular, I want you to focus on something called the call stack. Now, we haven't talked about this before, but the call stack is a list of all of the methods that are currently running in your program and waiting to finish. Now, when we first start out, the only method that's waiting to finish is main, but main is going to call count. So let's step into count. So now we have a call to count, which is running on top of main. Again, this is a stack, which means that we have to finish running count before we can keep running main where we left off. And in our count method, if we step through that one at a time, so in this case, m is 1 and n is 5, so we're going to jump into the else. We're going to print the m, so we're going to print 1. And then we're going to call count again, but this time with m plus 1 and n. So now, notice here, we have another version of count. on our call stack. We're not finished with the first one. We put that one on pause, and we're going to come back to it later. So now we have one version of count from 2 to 5. We've still got an old version running that's on pause, that's from 1 to 5, and we also have main. But if we get back to where we are in count, so count again from 2 to 5 is going to jump in and count from 3 to 5. And here, let's jump ahead a couple times. So we're going to do count from 3 to 5, count from 4 to 5, count from 5 to 5, and we're even going to run count from 6 to 5. So if you take a look at our call stack, for example, again, we've got 6 copies of count. Each one of them has its own set of parameter variables. And you can see that if you look at what's in the stack. And all of those methods, except for the top one, are on pause, waiting to finish. Now let's see what happens. So when we count from 6 to 5, again, in the if statement, there's nothing to do. So we're going to skip down to this print statement, which I just put in there because I wanted you to see what happens. So now we're going to finish counting from 6 to 5, and watch what happens. That number 7 pops off the top of the stack, and now we have to resume counting from 5 to 5 where we left off. Well, where did we leave off? Well, we had just printed 5. We had just called count from 6 to 5. So we're finished with the else, and now we're going to run this print statement. So counting from 5 to 5, we have to run that print statement, and now that version is done, and now that version is done, and now that version is done, and so on, and so on, and so forth. So it's really important that you understand this idea that every time you call a method recursively, it creates a new copy of that method and puts the old copy on pause until it finishes. And you can end up with, an innumerable number of method calls depending on how complicated the solution is that your algorithm is trying to figure out. Okay, let's get back to our slides. So what's the point? I mean, no one's going to sit down and write a computer program to count recursively. But there are several other problems for which recursion can actually make what seems like a hard problem a lot simpler. One example is the first lab that you're going to do, which is the Towers of Hanoi. If you had to sit down and write down the optimal sequence for solving that game just by listing out all the moves in order, it would be really hard. But it turns out that we can write a very simple recursive solution that summarizes the technique that you would use much more naturally than if you had to try to translate it into some non-recursive solution. If you think about it, you probably have a lot of situations in your life where you might solve a problem by doing a little bit of work and then trying to solve the smaller version of the same problem. And that's where recursion really comes into play. It can make your code a lot shorter, more elegant, and actually easier to understand. It's not to make you look cool, okay? Don't use recursion just for the heck of it. You should use it only if it makes your programs more sophisticated and makes your solution easier for people to understand. Okay, contrasting recursion with what we've been doing up to this point, which is iteration. Recursion, like we've said, is when you have methods that call themselves. Usually recursive methods, and we'll look at this in a minute, the syntax involves if and else statements. You don't need looping because in essence the recursive calls act like a loop. When we had 6 copies of our count method there, that was the same thing as if we had a loop that ran 6 times. So you don't usually need to have a loop in order to make your recursive method run over and over again. The opposite of that is iteration. An iteration is a solution that involves repeating, but it involves using a loop and not recursion. Typically, not always, but most of the time, if you have a recursive solution, you can turn it into an iterative solution, and vice versa. Most iterative solutions that involves loops, you could, if you had to, write as a recursive solution. When we deconstruct our recursive solutions, we'll see that each recursive solution consists of 2 main parts. One of the parts is called the base case, and that's the part of our program where we're not going to do recursion. If you want to think about it, it's kind of like we've reached the bottom. We've reached the end. We've reached the point where we can't make our problem any simpler or any smaller. And typically what happens when you reach the base case is you do a little bit of work in order to finish the job, and then that recursive call is done, and then you jump back to the previous copy of your method. The opposite of that is if you're in the recursive case, and that means that you still have more recursion to go. Every recursive case has to include some small amount of work. If you don't do any work, then you're never going to get any closer to the solution. So you do a little bit of work, you call the method recursively, and it's really important when you call the method recursively that the recursive call gets a little closer to reaching the base case. Because if the recursive call doesn't get you any closer to the base case, then you're going to get stuck in infinite recursion, which is the recursive equivalent of an infinite loop. If we look at this count method that we were just looking at, you can see that the if statement, which is when we reach the end of counting, is the base case. And in this case, there's nothing to do. Sometimes that's the way it is. We could really rewrite this code without that, but I left it in there just to make it a little clearer. In the else here is the recursive case, and we do a little bit of work by printing out the number, that's m, and then we call the method recursively. In general, a recursive solution is going to have a form like the one you saw. There's going to be an if statement, which checks to see if the base case is true, and if it is, it does base casey stuff. And then an else, which means that the recursive case is true, and then you have to do recursive casey stuff and then call your method. Sometimes you call your method first and then do the work. Sometimes you do the work and then call the method. It really depends on the kind of solution that you're working on. A couple more little tips. If you're writing a method with a return value, then you have to put the return value in the base case, and you also have to make sure that you have a return statement in the recursive case, because eventually you're going to reach the base case. You have to return something back to the previous version of your program, and then in the recursive case of that previous copy, it has to take that value that you returned, do something with it, and return something else. Again, I can't stress this enough. Make sure that when you make your recursive call, you move a little bit closer to getting to the base case. So if you're doing Towers of Hanoi, for example, hint hint, if you're going to solve the 5 disks problem, you should try to figure out some way to solve the 4 disks problem. That's going to have to be a cornerstone of your recursive algorithm. Okay, so there's a lot of stuff in this lesson to think about. You're going to get a lot of practice. We talked about what recursion is and an example of how it works with creating copies of the method that stack on top of each other. We talked about why you'd want to use recursion and how it contrasts with iteration, and then we talked about the basic syntax and the parts of most recursive methods. All right, you're all set.